Hello, welcome to Testing Synchronization. My name is Fraser Mort. I'm one of the business development executives here at Calnex. So just to give you a little bit of background information into Calnex, we are an industry-leading test company for new Sync over Ethernet technologies, including PTP, Sync-E and NTP. We do show leadership in the standard bodies. We've been active members for some years in the ITUT study group 15, and until recently we have been chair of the ITUT study group through Jean-Louis Ferrand, but he's now retired now. We also sponsor John Eidson, who's working on the new version of 1588 version 2, which is version 2 2016. And we also support him in that work as well, so we sponsor and collaborate him on that work there. We do hold a relatively large market share, selling into all leading equipment manufacturers, including component and clocking vendors, but also all major operators as well. And we are the de facto standard for test equipment for Sync-E, says 1588, NTP and some OEM testing. Okay, so today we're going to be talking about the Paragon X and Sentinel. Now the Paragon X is our totally integrated test solution for testing to the latest ITUT standards and proven performance of network equipment to new sync over packet technologies in the lab. Now the main event, our Sentinel, is our dedicated field sync analyzer. So synchronization in the mobile backhaul, what is it that mobile networks need? Now we have this requirement at the air interface. At the air interface, which is plus or minus 50 parts per billion for frequency. Now in the backhaul we have to be 3 times better for frequency, so that leaves us with a 16 parts per billion requirement within the backhaul spec. So in order to make networks work and to avoid any issues, we need to be meeting this plus or minus 16 parts per billion requirement. We are seeing a further requirement for time and phase, which is at 1.1 microseconds at the backhaul spec, and this is largely being driven by the introduction of small cells. Now small cells need to cooperate with the backhaul networks themselves, and small cells have a requirement of 1.1 microseconds, but they need the networks themselves to actually have a certain technology of LTE-A advanced, for example EICIC, and these two need to work together. For that to happen, they need to be synchronized to 1.1 microseconds. So not meeting all the above specs will cause mobile service issues. So what sort of issues are we likely to see? So in a frequency-based network, for example WCDMA or LTE-FDD, the key IP network issue we'll see is going to be a high PDV. Now this PDV is caused by routing, congestion, and traffic behavior. Also interested in performance of specific equipment, PTP Grandmaster, performance of the slave with regards to your best master clock algorithm and clock recovery. To help us assess this, we have ITUT masks for our PDV limits, or FPP is a mask I'll talk a bit about later on, and these metrics and limits are taken from G.8261.1. Phase synchronization, for example small cells or LTE advanced. The type of network issues we're going to see is going to be the asymmetry delays, and this can be in the equipment and link, but asymmetry is something that's very hard to compensate for. Again, performance issues regarding the PTP Grandmaster and the slave with clock recovery algorithms. Limits for phase and frequency from the ITU-T limits are 1.1 microseconds as mentioned before, and these are found in 0.8271.1. So the ITU-T have a set of standards or recommendations for both frequency and time and phase packet synchronization. So on the left here we have our standards recommendations for frequency, which is our 0.8261 set of recommendations, and on the right we have time and phase or 0.8271 series of recommendations. Now, what 1588 has introduced is the notion of PTP profiles. And these profiles specify the use of 1588 version 2 for specific applications. And for the telecom application, these profiles are different for frequency as they are for time and phase. So for example, the 8265.1 is the PTP profile for frequency transfer. And this will define such things like unicast modes, IPv4, VLANs are allowed. It's an end-to-end mechanism. It will have message rate specifications, like a flexible message rate, and it will have an alternative best master clock algorithm specified as well. And comparing this to the time and phase, 8275.1, this is a multicast operation with layer over layer 2. The specific message rates have to be exact. No VLANs are allowed, and allows the use or specifies the use of boundary clocks. Now you'll notice that there's two different profiles here. One for full timing support, where every element in the network is 1588 aware, and it also has a recommendation or profile for a partial timing support, which is 1588 aware devices at every occasional node throughout the network. So we also have network requirements in here, and again, one for frequency, one for time and phase. 8261.1 is our network limits for frequency synchronization. So in here will be our PDV limits and also our clock recovery. For time and phase, this is where our 1.1 microseconds comes from, and again, one for full time support and partial time support. Within these standards here, we'll also define reference points and limits to each of these reference points throughout the network. Some operators like to do acceptance testing before elements go out into the field. So for this, you'll be looking at clock specifications. Now what this does is characterize individual bits of equipment for both time and frequency. So for the frequency side of things, if you're running Sync-E and you want to characterize a Sync-E equipment slave clock, then 8262 would be the recommendation there, and if it's packet-based equipment clock, then 8263 would be that specification there. Within time and phase side of things, we have different recommendations for different elements, so grandmaster, boundary clock, transparent clock, and assisted partial timing support. Now some of these are still in development, and the boundary clock is finished, so within these it characterises the behaviour of a boundary clock in the network, and likes of assisted partial timing support. This is where GPS is used alongside PTP as timing support. So what I'm going to talk about first is a network delivering frequency synchronization only. So with no traffic, the PTP messages can transfer through the network with minimal and probably constant delay, in which case the slave will have no difficulty in recovering the clock. However, as the traffic and congestion in the network increases, the PTP messages will be buffered and queued inside each switch or router. and each message will be delayed by a different amount depending on the traffic at that instant in time. This is what we mean by packet delay variation, or PDV. The PDV will increase as more hops are introduced and or the network becomes more congested. And the higher the PDV, the more stressful it is for the slave to recover the frequency from the PTP messages. So in a network full of non-1588 aware switches, PDV can be significant, and of course slave clock recovery can be a challenge. So in G.8261.1 defines network limits at certain reference points throughout the network. Now what we'll be interested in is reference point C. Now this is our Ethernet interface at the input to the slave, carrying the PTP messages. And the limits at this point are our PDV limits. So these are defined, or the PDV is defined in terms of a floor packet percentage. Now I'll come on to this a little bit later in more detail, but basically it needs to pass this limit to ensure that the slave will be able to recover the frequency from the amount of PDV through the network. At reference point D, this is our output of the slave, or clock output from the slave, which could be a 2 meg, could be an E1, and perhaps a 10 meg. And at this point we want to be making sure that these clock outputs are within our 16 parts per billion requirement. So now I'm going to be talking about time and phase synchronization within networks, and also time error. So the time error of a clock is quite simply the difference between the time indicated by that clock and of a reference clock. Now it's very important that there is a reference involved. So the measurement itself, or time error itself, is always relative and it has no meaning without a reference. It varies with time and can be expressed as this rather complicated function. However, if we have a frequency locked, or if we are maybe using Sync-E as our frequency transport, then what this reduces the time error to is constant time error and a dynamic time error. So time error and time interval error. Time error measures the time difference between two clocks, and what we have is three measurement parameters within time error. So we have the maximum time error, which is the maximum distance from zero. We have constant time error, which is our network asymmetry, or an average time error. And we have dynamic time error, which is our random variations and noise through the network. Time interval error measures the change in time error. Now this is maybe a familiar concept, but this basically tracks the dynamic time error over time. So we mentioned before, we do need an accurate reference to measure time error. If the measurement doesn't have a reference, then we can only estimate the change in time error, but we need to measure it, so we need an accurate time reference. Ideally the reference should be the same reference source as the grandmaster in the network. And the measurements must be filtered to remove any jitter. A maximum time error is maximum distance from zero. Constant time error is the average and is the asymmetry. Dynamic time error is analysed using MTI and TDEV and is a random noise through the network. So network limits at the reference points. What we're interested in is maximum time error, specified in nanoseconds, and dynamic time error. For individual equipment clocks, we're interested in asymmetry through the equipment and also the dynamic time error. So within G.8271.1, it defines a time error budget. And this budget goes from the grandmaster all the way to the air interface, which is 1.5 microseconds, But within the backhaul, so basically up to the input to the slave at reference point C, it's 1.1 microseconds. And within here we're allowed to have no more than 11 nodes, each producing no more than 50 nanoseconds of time error, or constant time error. Now we don't have to use 11, we can maybe use 5 or 6, and what this will leave us with is more budget for link asymmetry, which we are compensated for about 250 nanoseconds worth of link asymmetry. Now link asymmetry is something very difficult to compensate for. For example, if it was an optical network and you had a problem with one of the optical links and it needed to be repaired, so you had to splice the cable itself and repair it and replace with more cable. So for example, 1 meter extra of cable was added to one direction of link. 1 meter is equivalent to about 4 nanoseconds of time error. So right away we have an asymmetry that we had to try and compensate for. As you can see as well, even the grandmaster itself has some time error. So between your PRTC and your grandmaster, we're at 100 nanoseconds of time error. And for our random network variations or random noise, we're allowed 200 nanosecond dynamic time error. Also defined in 8271.1 is our reference points again. So at reference point C, our input to the slave and output to the slave, and we have our 1.1 microsecond limit that we need to reach. Now on the input to the slave, we measure this time error on the packet or the Ethernet interface using the timestamps, and on the output of the slave, we measure the time error on the 1 PPS. So as a network test strategy, what we've seen in the past and what our experience shows is that operators do like to do testing on individual bits of equipment in the lab and verify them before they're deployed into the network. And as they deploy them into the network, they'll use sort of cheap handheld turnip testers that can do some basic quick sync testing and give us an indication at that point in time what's going on in the network. And if we sort of see something that we don't quite understand or don't quite expect, we need to start to do maintenance and troubleshooting with a dedicated sync analyzer. This needs to be the case because we need to do long-term measurements to really understand what's going on in the network. And the ability to send captures back to the lab is an extra added bonus and helps us in maintenance and troubleshooting. So once it's all deployed, we have maybe built-in monitoring systems within the eNode Bs themselves, and these will tell us if something is not right. So if we're maybe out with our 1.1 microseconds, or if our PDV is too large. So it's an alarm. So what you can do is think about these management systems as alarms or a fire alarm, and when one goes off, we need to tackle that fire. So this is where we go back to step number 3, using a dedicated sync analyzer to drop into the field and do long-term detailed sync analysis. So our Paragon-X is our flagship lab testing equipment. This is a fully integrated solution for evaluating individual PTP equipment clocks and sync equipment, and specifically 2 ITU-T standards such as 82826X series and 827X series, but also sync standards as well. Now, one of the key aspects of this is our master-slave emulation. Now, the way we use this is to fully stress improve limits of each network element that delivers synchronization over a network. And we can do this by capturing PDV from a network and then replaying these in a controlled environment in a lab to stress and improve this equipment. It allows complicated test beds to be made highly repeatable and much quicker to set up. So what do we mean by a fully integrated solution? Well, using this boundary clock testbed as an example, now this is a recommended testbed setup from the standards itself. And as you can see, it is quite a complicated setup. But more importantly, remember the slide with the budget on it, how we have 100 nanoseconds allowance of time error for the Grandmaster itself, and we had some for the slave. So before we even start the test, we have 100 nanoseconds of uncertainty within the test. And then of course we have all the cabling. On electrical cabling, we're probably about 4 nanoseconds of error per meter of cabling. And if there's quite a lot of cabling in here, then that may introduce some error in the test bed itself. So we need a master, we need a slave, we need to be able to set up a session and send messages through in both directions. We also need to be able to impair in both directions as well. And then we need to measure, and we might even have a GPS emulation as well. We may need to use some taps, which makes the measurements more uncertain as well. So the challenge here is to prove the PTP within this network to G.827X series of standards. So we can see right away that this is a complex setup, and this complexity introduces our inability to repeat this test accurately. So repeatability is an issue, and this may take a long time to set up if you want to do the test over and over again. So our solution, being the Paragon X, actually integrates all inside the Paragon X itself. And because these elements are inside, we get rid of that 100 nanosecond time error we would see in the Grandmaster. Because the master and the slave share the same time base, this makes our measurements very, very accurate to within 5 nanoseconds. So there goes our equipment's uncertainty. Now also goes the cabling. So we don't need all of that length of cabling, therefore we can reduce cabling uncertainty and be left with very limited cabling, where we can actually factor in the length of these cables in the Paragon X GUI. So it's an integrated solution, it's faster to set up, it's highly repeatable, and it's highly reliable due to the uncertainty that we've eliminated. Okay, so now I'll move on to our Sentinel platform. Now Sentinel is our flagship field sync analyzer. And what I mentioned before in the time error measurements is that it's vital that we have an accurate reference, and this is the same story for frequency and PDV measurements. Now one problem in the field is that some base stations are in basements or perhaps in urban canyons, and therefore a GPS reference is not available. So inside the Sentinel we have a GPS rubidium with a battery holdover. So what we can do is we can train the internal rubidium overnight and then put it into a transport mode, which will keep the rubidium warm, and then when we travel to site we can plug it in and we can actually use the rubidium in holdover to do very accurate time error, frequency or PDV measurements. We have a very easy test setup. We have a signal wizard inside the Sentinel. So whatever we have plugged into the box, whether it's a frequency, 1 PPS, PTP, sync E, it will detect exactly what's connected into the box and let us know the status of these links that we have, and then we can start the measurements from there, and we can do all the measurements at the same time. So we have a clear pass-fail criteria built into the Sentinel, so we can actually see the results progress in real time and see them progress against the standards. So we have the ITUT masks built in, plus specific vendor limits as well. Now one key aspect of the Sentinel is its capture ability. So we can capture PDV in the network, and then we can replay and measure the network back in the lab on a Paragon X. So I'll talk a bit about this later, of how Sentinel and Paragon-X can be used together. I'll also talk a little bit more about the report generation and the remote operation of Sentinel. So the Sentinel has two modes of operation. We have the Pseudo-Slave mode, which allows us to connect to a Grandmaster, set up a session and measure PDV through the network. We can also measure time error on this interface as well, using the PTP timestamps. So you notice here we have the antenna, so we can either be connected directly to GPS, or we can be running off the rubidium in holdover. Simultaneously, we can also be measuring 2 meg, 10 meg, or 1 PPS. We can actually measure any frequency from 0.5 Hz to 200 MHz, and we can do this at the same time as measuring our PTP. And it's worth noting that we can also measure sync E, if there's sync E on this line as well. We also measure sync E at the same time as PTP. We can also connect to two separate Grandmasters. So if there's a protection architecture system built into your network, we can measure the PDV and time error on each path through the network. At the same time, we can also be doing frequency and 1 PPS measurements. Our second mode of operation is a monitor mode. Now this allows us to use taps or splitters within a network. So if you wanted to test the PDV in a different way, i.e. the actual packets going from the switch to the base station, you can use taps or splitters and do a PTP measurement that way, and again taking a frequency or 1 PPS measurement from the base station. This is also how we do NTP testing with the Sentinel. We don't have an NTP client within the Sentinel yet, so if it's NTP you're testing, monitor mode is the way we do that. So you want to do a few things with the Sentinel. You want to test before deployment. So if you're maybe building a new network, or you're introducing more routers, extending the range, or introducing new slaves, you want to evaluate what your network's doing before you actually deploy. So in the example where the eNode B is not deployed yet, or there's maybe not a provisioned port, we can use the Sentinel and the Pseudo-Slave mode to connect to the master, and we can measure PDV through the network. So by doing this, we want to just make sure the network is ready for frequency synchronization. So we want to make sure it's within the limits, and we measure the PDV out of the network at reference point C, which is our input to the slave, and we measure it against ITU-T or vendor-specific metrics for PDV. And again, if there's no GPS on site, we can use the rubidium in holdover. So an example of how the PDV would look on the Sentinel, and this is a PDV measurement. So in the link here, it tells us what this channel is connected to. So we have a 1 gig electrical connection. We have sync E running as well. So we're seeing a quality level of PRC. Our PTP session is unicast, domain 0, UDPO over IPv4. It's a one-step clock. We have message rates. We have the master we're connected to and the clock class of that master. So it gives us a summary of what we're connected to here. Now it's ideal to capture for greater than 24 hours. This will give us a full picture of what goes on with the network throughout the day. And the Sentinel is capable of doing longer than 24-hour measurements. So now we have our PDV measurements. We need to actually make sure this is good PDV, and this is where we apply the metrics. Now, this is just one example of our of the ITU-T metric FPP, which is a floor packet population or floor packet percentage, which is found in 08261.1. Now what this says is that 1% of all packets must fall within 150 microseconds of the delay floor in a 200-second window. So if 1% of all packets are within this range, then the slave itself should be able to recover the frequency from the network. This is how it would look on the Sentinel itself, with a 1% limit line, and our results are well above, so that's a pass for that metric. So we would do the same thing for making sure our network is time and phase ready. Again, if B is not being deployed yet, we can use the Sentinel as a slave, and we can do a 1 PPS measurement out of the network. Now we can do this on the 1 PPS, but if the boundary clock or transparent clock doesn't have a 1 PPS output, we can also do a time error measurement on the PTP flow itself using timestamps. We have the mask built in as well, so we can make sure it's within the 1.1 microseconds. And again, we can use the Sentinel rubidium and holdover if we have no GPS connection on site. Just a quick example of what a time error measurement on a 1 PPS would look like. I do have an example of a time error measurement on the PTP Ethernet interface, but I'll come to that later on. Testing after deployment, so once it's all deployed and working, we need to do troubleshooting. So we need to troubleshoot sync-related issues and maybe do the occasional network audit. What we do with the Sentinel is can actually measure 2 separate points in the network at the same time. And what this avoids is finger pointing between the equipment vendors and the slave vendors. So by doing this, we can simultaneously measure PDV on the input to the slave and the recovery clock on the output of the slave. And for during deployments, we use the Sentinel in the same way. So by doing simultaneous measurements, we can measure PDV and time error on the input to the slave at the same time, and analyze it with the metrics. And we can also simultaneously measure phase or frequency output of the recovery clock. So as mentioned before, we can actually operate the Sentinel remotely. Now the thing with network issues is that they're always intermittent, so they're never predictable. And what can be a good idea is to actually set up the Sentinel at your base station on a semi-permanent basis and hook it up to your network and to your Grandmaster. And you can actually remote access to set up the measurements, start and stop them. And of course we can actually download the measurements or we can FTP the measurements off of the Sentinel and analyze in our offline tool, the CAT software. So to talk a little bit about our CAT software, our Calnex analysis tool, and this is our standalone application that runs on Windows. Now this can be used across all of our products, so Sentinel, Paragon X, Paragon T, and soon Paragon M as well. And what this does is analyse E1, 2 meg, 10 meg wonder measurements to ITU-T masks. We could do time error of the clock outputs, whether it's 1 PPS or on the Ethernet interface. PDV metrics, including ITU-T and vendor specific masks, and we can do sync E measurements as well there. So the results from Sentinel can be analysed in more detail with the CAT software. So like I mentioned before, we can FTP the results off Sentinel and analyse using the CAT software. Or we can save them to a USB from Sentinel and analyse in CAT. And of course, report generation, I'll come on to this a little bit later. So just as an example here, now this is a PDV measurement taken from the Sentinel and loaded into our CAT software. So as we can see, we've got a PDV measurement, but it doesn't actually tell us much about what's going on, so we don't know whether it's good or bad PDV. So what we do is we select on the left hand side here which metric we like to use. So here we have MAFI selected. If we could scroll down, we would see the FPP selected. And when we select it, they pop up here in tab, so we have the FPP there. Then we hit calculate, and this will bring us to the results of this PDV. So now we've hit calculate, and we now have the results of these metrics we selected on the side here. So if we look at our FPP, which is selected, we see our 1% limit line, and the results in the both forward and reverse directions are a pass. And we have the parameters down here, which we can adjust ourselves, but this is also because Huawei have a very similar metric. It's just slightly different parameters. I think for Huawei it's 100 second window size, floor delta is 100 microseconds, and I think 10% of packets need to be within this limit. So, but we can change this ourselves here. So dynamic time error we can do as well with the 0.1 Hz filter applied, and we can set the masks, and again gives us an instant pass-fail indication. And we can also do constant time error or network asymmetry. So I mentioned before, report generation. It's quite a unique and important feature. Allows you to automatically generate PDF report, include graphs, tables, pass-fail metrics, whether it has passed, whether it's failed. And these are ideal for printing off and distributing internally, or perhaps you can send to the vendors themselves for them to troubleshoot issues on equipment. So I'll just quickly run through a short case study using Sentinel. Was a Tier 1 operator ready to deploy a certain type of LTE-A in a stadium. So this is a 1.5 microsecond end-to-end limits, but the customer was actually looking for something a bit more stringent at 500 nanoseconds. So there was no PTP-aware devices in the network, and they haven't done any testing before. There's no Anode B, so there's no clock output, and the basement where they are, there's no satellite visibility. So these are a few challenges that the customer faced. So what we did was we connected the Sentinel in monitor mode. So what we're doing is we're measuring the PDV from this BC to this BC, and then measuring a 1 PPS at the same time out of here. So what monitor mode allows us to do is actually monitor the real network PDV seen by this BC. Now we also used the internal rubidium, so we trained this overnight. Now we trained it for about 12 hours. 12 hours is I suppose a recommended time for doing time error measurements, and then it was put into holdover for the measurement, and the Sentinel drifts 100 nanoseconds over a 24-hour period. So it's a very, very accurate rubidium, and will allow you to do time error measurements in the field. Results were as so. We had 1 PPS accuracy of 12 microseconds, which is well out with the requirements, therefore a red for fail. And the PDV results looked relatively normal. It passed one of the metrics, so the PDV looked relatively normal. So the high time error might be due to network asymmetry rather than a high PDV. So some key values that we took from this case study with the Sentinel is that operators need to evaluate networks sooner rather than later. When When implementing new technologies or new equipment into the network, we need to know what's going on prior to implementation of these new equipments. The 1.1 microsecond is a very strict specification, and we need an accurate tester to do the measurements. And the high performance of Sentinel rubidium made that possible to measure the 1.1 microsecond limit on site with no GPS available. So to sum up, fixing network issues is the Sentinel's key role, and measure and replay, or capture and replay, is something that really helps us to troubleshoot networks in a very timely manner. So we can capture PDV with the Sentinel, like so, and then we can replay on a Paragon X in a controlled environment to quickly evaluate what the slave clock is doing to your actual network PDV. So the true value of Calnex Solutions equipment is that the operators can do testing in their own networks. They can troubleshoot issues, but they can also send that data, those captures or their network capture, back to the equipment manufacturers for them to replay that in their labs in a controlled environment to troubleshoot issues with their equipment. So the value of Calnex is introducing this more collaborative approach between equipment manufacturer and operator to really improve the efficiency of troubleshooting within synchronization within networks. So thank you very much for listening. If you have any questions at all, my contact details are here on the slide. Some material is also available for download from our website, www.calnexsol.com. Thank you.